Okay, so example 2.1 want us to find the thermal efficiency for ideal Otto cycle. We know that we have two formula for thermal efficiency. One is the general one, work net over Q in, or we have another one that is we have already derived in our previous slide, 1 over RV. RV is compression ratio, K minus 1, where K is specific heat ratio, 1.4. So now RV is a compression ratio. The definition of the compression ratio is maximum volume over minimum volume, while K is specific heat ratio for air, 1.4. It's fixed, okay, throughout this chapter. Okay, now which equation or formula that we want to use to solve the example 2.1? For our first equation, we take a look that work net is actually Q in minus Q out. So for both Q in and Q out, for both Q in or Q out, we need to have constant specific heat, okay, and then the difference of the temperature. Either it is temperature 3 or 4 minus temperature 2 or 1. Okay, temperature at point 3 minus temperature at point 2 for Q in, and temperature at point 4 minus temperature at point 1 for Q out. So for this equation, if we want to use the first equation, we have to know the temperature. Okay, we have to find their temperature. But obviously, in this example, we don't have any values given for temperature. So therefore, we cannot find another value for another point of temperature. Okay, while in our second, if we want to use this equation, thermal efficiency, we know that in this equation, in this example, they give us a value of stroke, a bore. The bore is actually a diameter of the cylinder. So therefore, we cannot use this equation. Okay, cannot use the first equation because we don't know. We cannot have this temperature. And we will use this equation to solve the problem. Okay, now we know that from the data given, we have cylinder, have intake and exhaust valve, and we have piston here, and then they give us bore diameter with 50 millimeter, and then this is TDC, this is BDC, this is stroke 75. Okay, so In this example, they also give us the clearance volume. This is clearance volume, okay? Clearance volume of 21.3 centimeter cubic. And we have displacement volume here. This is, we call displacement volume or sweat volume. So, obviously, the maximum volume can be calculated if we add these two. If we add these two, if we add these two clearance volume and displacement volume, we can get maximum volume. So minimum volume is actually clearance volume. So if we can find displacement volume, then obviously we can solve this equation and get the thermal efficiency for this example. Okay, so now displacement volume of cylinder, we just need to calculate actually the volume of the cylinder. So volume of cylinder is pi r L. So R is 50 over 2 and L is 75. So if we substitute all the values and then convert all to centimeter cubic, okay, convert all to centimeter cubic, we will have 147.2 centimeter cubic. And then all we need to do is find the maximum volume. 147.2 plus 21.3, we will have 168.5 centimeter cubic. And then we will substitute this value to find compression ratio. We will get compression ratio of why we need to change all the units so that we can delete them. Okay, we can delete the centimeter cubic there, and then we have the answer for we can have compression ratio. The answer is 7.914. If we substitute to the above this first equation, we will get the answer of 56.3%. Okay, the point is, in this example, the point is you need to convert. Make sure that the unit is centimeter cubic so that we can cancel. It doesn't matter that if you want to convert to meter, also can. So the point is we can cancel this out and have the correct ratio. Okay, this is how we solve the example 2.2. 2.1.